So our second case study will be a two-pass seawater RO system. This one will be located in Saudi Arabia. It will be an open intake system with STI less than 5 and conventional pretreatment. Operating salinity will be 44,000 milligrams per liter, with feed boron of 6 milligrams per liter and a feed pH of 8. Operating temperatures will be between 20 to 35 degrees Celsius, with a permeate production target of 80,000 cubic meters per day. And recovery from the first pass can be between 40 to 43%, and recovery in the second pass can be between 88 to 90%. Maximum membrane age, again, we're going to be using 3, and the permeate TDS target will be 150 ppm, and the permeate boron target will be 2.4 ppm. So in this case, we also want to operate with 8 trains, so we need to make sure the number of pressure vessels that we're using is divisible by 8. And we also want to make sure that N-1 operation for first and second pass is available for the system. So that means we need to make sure that the plant works with 8 trains and with 7 trains in both first and second pass. Some additional design notes for this project. We want to minimize the energy consumption and the operating feed pressure to keep it as low as possible. We want an energy recovery device with 6% volumetric mixing. We want feed and permeate split. And also we're going to have a second pass brine recirculation to our first pass feed. So let's again switch back to our Q+ projection software. So here I have another tab open where I've already loaded in our feed salinity information. So you'll see here that the 44,000 milligrams per liter of feed salinity is already loaded in just to save us some time. Balance and save. And the next thing we want to check again is the feed source. So the water source that that's selected by default is seawater open intake. So that's acceptable for this system because we're dealing with an open intake system with conventional pretreatment. Temperature, again, we're going to go to the maximum temperature because this is where we want to see if our design can meet the permeate quality requirements. Because this is a 2-pass system, I'm going to add the 2-pass. Add the second pass by clicking Add Pass behind the first pass permeate tank. So for our membrane age, we're going to be using 3 years as the maximum membrane age for the first and the second pass. We're going to change the units again from meters cubed per hour to meters cubed per day. In this case, the permeate production target was 80,000 cubic meters per day. First, the recovery of our first pass, it was between 40 to 43%. Because one of the notes in the for the design was to minimize the energy consumption and the operating feed pressure, I'm going to be going with a lower recovery of 40%. For the second pass, recovery does make a slight difference in feed pressure, but it's not that big compared to the first pass typically. And also in the second pass, usually if you go with 88%, that means that you're a little bit concerned about your permeate quality. 88% will give you a little bit better permeate quality than 90%. However, in this case, let's just use 90% because we do have the second pass and we're going to be using a front feed and permeate split. We're not too concerned about overall permeate quality. Permeate TDS of 150 ppm is not that difficult to meet in a 2-pass system. So for a permeate production, let's just set this the reason I'm selecting 88,888 is because if you have a full second pass with 90% recovery, that 88,888 from the first pass becomes 80,000 after the second pass. So we're going to add in a second stage for our second pass. Typically, when you're using a two-pass system, your second stage will operate with two stages in order to maximize the recovery. In this case, because it's 90%, it's much too high for a single stage. So we're going to be using a two-stage system. Another thing we wanted to add in was our energy recovery device. In this case, we're going to leave the volumetric mixing at 6% again. And our recirculation, we're going to add in as well. You choose the start point for your recirculation, which is your second pass brine, and it's going to be recirculated to your first pass feed, which is the target point selected here. And then for the concentrate flow, I'm just going to be using a percentage. I'm going to be using 100% to recirculate all of the brine. So now we need to make our membrane selection. Again, when you click the drop-down menu, you have different membranes available. You have SR, GR, R, and ES. ES is our energy-saving membranes, but it's typically not suited for these higher salinity conditions and higher temperature conditions. So in this case, we might want to use a high rejection membrane. Because we wanted to minimize energy consumption, I'm going to be choosing one of the higher flow rejection membranes, which is the SWR. And I'm going to be using the 440 square foot membrane. For the pressure vessel length, I'm going to do 7 again. For the second pass as well, I'm going to change it to 7 elements per pressure vessel. And for the membrane choice, I'm going to go to our brackish water membranes. And I'm going to be choosing the 440R, which is the high rejection brackish water membrane. So the next step again now will be to change the number of pressure vessels in order to get an average flux closer to what we're comfortable with. In this case, with a seawater open intake system, the average flux that I would typically want to target would be around 12 to 13 LMH. So let's just change the number of pressure vessels in order to get somewhere our first pass flux to around 12 to 13. Another thing to keep in mind, we want to keep it divisible by 8 trains because, again, this plant will have 8 trains, so we want to keep the number of pressure vessels divisible by 8. So let me first start with 400. And you can see here the average flux changes to 32 LMH, which is still really high. We want to get it to around 12 to 13, so we do need to add additional pressure vessels. So let me go to 800. And now it's at 16. Let me add a little bit more. Let's try 1,000. So we go to 1,000, and now we're right under that 13 LMH max that we wanted. So that could be acceptable. So let's just start with 1,000, and then maybe we can play with it later on, or maybe it will be okay. So now we want to change our second pass pressure vessels. For second pass flux, you typically want to target around 30 to 34 LMH. One thing to keep in mind that when you do change from n to n-1 operation, the flux will increase. So in this case, because typically we're going to go 30 to 34 LMH, but because there's an n-1 operating condition, instead of targeting the higher end, maybe we want to get closer to the lower end, somewhere around 30 LMH. So for the number of pressure vessels, let's try 400. And we see here the flux is around 29 LMH, and so that's a good starting point. So let me change this to 300 and the second stage to 100. So as I mentioned, we want to keep it divisible by 8 when we have our final design. However, right now in the beginning, I just want to check our permeate quality to because I know we're going to be making a lot of changes to the number of pressure vessels. I want to see the permeate quality and then that we have right now, so we can determine how much permeate split that we might need first. So once we hit calculate, because this is a 2-pass RO system, the calculation does take a little bit longer than a single pass seawater system. So once the design is finished calculating, you can see now your permeate TDS is approximately 20 ppm, a little bit lower than 20 ppm. Our permeate target was 150 ppm and our permeate boron target was 2.4 ppm. So we do have a lot of room for changing this. So let's go to permeate split in our design tools, and it'll give you an indication that you can change. You can add in either the normal permeate split, the simple split from the tail, or you can use the feed-end split. In this case, we want to use the feed-end split as specified by the design requirements. And instead of targeting the flow, we're going to use a percentage. So in this case, let's try 20% first, and then just see what permeate quality we're going to get. And you'll notice the flux for the second pass is much lower now, and also the production will need to change. We'll get to that in a bit. First, we just want to eyeball, get into the general range of how much permeate split we're going to target. So with 20%, and once we hit calculate, we can check our permeate quality again. Now we see our permeate quality is around 70 ppm TDS and 1.6 ppm boron. So we do have, again, room to increase the permeate split. One thing that we want to consider is the safety margin. So in this case, let's just say the client wants to consider approximately 30% safety margin. On 150 ppm TDS, 30% safety margin would be about 115 ppm. And on 2.4 ppm boron, 1.3 safety margin would be about targeting 1.85 ppm boron, right? So if we want to keep it within 115 ppm TDS and 1.85 ppm boron, we still do have room to increase the split. So in this case, let's increase it from 20% to 35%. And now we see our flux is quite low. Let me just change this real quick. Let's try somewhere around 160. And 48. And the system flux for the second pass is a little bit high still. So we do want to make some changes to that later. But again, right now, we just want to check the permeate quality first to see if we're in the general ballpark of the permeate quality we want to meet. So in this case, we see that the permeate TDS is still under 100, and our target was about 115, and our permeate boron target was about approximately 1.85, so we still do have room there. So what this means is we can increase the permeate split a little bit more. So let me increase this to, let's say, 40%. Okay, so now our permeate TDS is right under 115 ppm, and our permeate boron is still farther from the target. So in this case, permeate TDS will be limiting. Let's just adjust our permeate flow first in order to get the 80,000 cubic meters per day of total production. And then we can change this to so you notice now the flux went from close to 13 to around 12.4 LMH. And we'll see if we need to make any additional adjustments. Okay, so we changed the production, and then now we see the permeate TDS is a little bit above 115 ppm now. It's at 118. So let's adjust the split down a little bit more. So from 30%, let's move it to 38, 40%, let's move it to 38%, for example. And we need to adjust the production as well. And then once we adjust the production, another thing that we want to adjust is the second pass. So the flux is at 33 LMH. We want to target the low 30s just because we want some room when we change to N-1 operation. So we do want to increase the number of pressure vessels. So for here, let's change from 48, let's go to 56. So it's still divisible by 8. And for 160, instead of 160, maybe we want to go to 168. So when we hit calculate, we see now we're under the 115 ppm TDS target. We're under the 1.85 ppm boron target. So we're meeting the permeate quality requirements for the system. We also have allowed for 8 trains of operation, so 1,000 PVs in the first pass, divisible by 8, so that would be 125 pressure vessels per train. And in the second pass, 168 divisible by 8, that would be 21 pressure vessels per train in the first stage. And for the second pass, 56 divided by 8 would be 7, so that would be 21 to 7 pressure vessel array for our second pass. So that number of trains is also divisible by 8. So this design works right now for N trains. Another thing that we do want to account for, as we mentioned previously, is N-1 operation. So when we have N-1 operation, we want to make sure that the system flux is still acceptable for the system. So for the number of pressure vessels, we're going to go from 1,000. If we're going to go from 8 trains to 7 trains, that's going to be 875 pressure vessels. And in the second pass, if we're going from 8 to 7 as well, I'm going to change the number of trains, 147, and from 56, we're going to go to 49. So you'll see now that the average flux is much higher in the first pass at 14.2 and also in the second pass at 35. However, due to the higher flux, you'll notice now that our permeate TDS is much better as well. So because we are operating a higher flux, something we can do is we can increase the split. When we increase the split, we can adjust the production as well after that, and then it'll help us reduce the flux a little bit. So from 38%, let's try 42%, for example. So when we go to from 38% to 42%, we'll see now that our permeate TDS is right under that 115 ppm target again. So that would be an acceptable permeate split percentage. And now we need to adjust the permeate production as well, just to make sure that it's aligning with the 80,000 cubic meters per day target. So now we've adjusted the production and we hit calculate again. And you'll see now the second pass average flux is much more reasonable. Instead of 35, it's around 33. And we're still meeting the permeate TDS with the safety margin of approximately 115 ppm. Another thing that we do want to check when we're operating at N-1s is obviously the maximum feed pressure. So the maximum feed pressure would be at 20 degrees, which is the minimum temperature for this project. So we hit calculate. So at 20 degrees Celsius, our maximum feed pressure would be approximately 63.9 bar. So that would be a good estimate for your maximum feed pressure. One of the things that you can change when you're operating at minimum temperature is your split percentage. So you'll see here, now that our permeate TDS, previously we were targeting less than 115 ppm at max temperature. If you don't adjust the permeate split, then you'll notice that now we're greatly overachieving in terms of permeate split, right? So something you can do at minimum temperatures, you can increase the split a lot in order to reduce the amount of flows being sent to the second pass and reduce the second pass size. And so you're not operating with more second pass trains than needed, for example. So that's something you can do. Another thing that we do want to check is at the maximum temperature. You want to check at startup at 0 years in order to see if there's any high flow warnings or any recovery warnings, for example. So we want to make sure our system works both at startup and at max temperature and at max age. So in this case, you can see here that we do have warnings in both the first and the second pass. So let's just check the second pass first. The second pass has a maximum recommended flux of 47.5 LMH. If you click here, we see that the flux is quite high. Instead of 47.5, it's at 50.5. So something that we can do to counteract this is you can add a little bit of permeate back pressure in order to solve this issue. So permeate back pressure does help you adjust the flow balance a little bit in the second pass. However, we don't recommend you do this for every case. This is more of a case-by-case thing. And now you'll see it went from 50 to 48.8, right? And our target was 47.5. So maybe in this case, we want to increase the permeate back pressure a little more. So in this case, if we increase the permeate back pressure to 2, for example, it'll help with the second pass first stage flow balance, and we can get rid of that warning. Now, if we take a look at the first pass, we'll notice that the flux is a little bit high at 34.73 LMH. And you see that, oh, excuse me, this is at 38 instead of 35. Let's change this back to 35. So we see our recommended flux values at 32.3 LMH. And in this case, it's a little bit above at 33.38, right? So it's about 1 LMH higher than we want. So in this case, for the first pass, adding permeate back pressure is not going to affect the flow balance. What we want to do in this case, one of the things that you can do is you can switch to a hybrid design, for example. You can hit the plus over here. So we want a tighter membrane in the lead. So we'll go to GR. And then the tail will keep all of the R elements the same. So if you switch to a hybrid configuration, for example, you can minimize these, you can help get a better flow balance in your system and minimize these issues. So in this case, we noticed that we had a warning, so we wanted to switch to a hybrid. So if this is the design you want to proceed with, if you want to maintain that hybrid, now you would have to go back to the end trains design with 8 trains, and you would have to readjust the permeate split, for example, and all of the other design choices that you made in order to optimize based on the hybrid design. So maybe now you can increase the split slightly because you're getting better quality using GR instead of R in your lead elements. So that is part of the process. Sometimes you'll notice some mistakes here and there that can cause you to want to change your entire design, or sometimes maybe the warnings could be a little bit acceptable, right? So in this case, let's just imagine that we're going to maintain 7 elements of our SWR. Because this is N-1 operation, it's not a typical operation point, because when you're operating with N-1 trains, Typically, this is usually only for cleaning. And with seawater systems, most of the time, you're not going to be cleaning too often. It's maybe going to be 1 or 2 times per year. If you're not going to be cleaning within the first year, let's just say the first cleaning will be at the end of the first year. So that's the first time the N-1 operation condition will occur. So when we change this to membrane H1, and we hit calculate, now you can check on the flow balance. You'll see 32.3 is the target, and we're at 32.33, right? So we're basically right at that limit that we were trying to target. And there's not going to be, and because this is because we made the assumption that we're not going to clean within the first year, because we're just right at that limit, maybe this can be acceptable for your system, right? So this really depends. Sometimes warnings might be something that you can be acceptable for your system, and in other cases, maybe warnings are something you want to remove completely, right? So we do have options in how we want to approach this. Maybe this design would be okay. However, if the end user, for example, is concerned with operating with any of these warnings, then we do want to switch to the hybrid design, right? But in this case, let's just say the design is acceptable, and we'll go back to our PowerPoint. So this is approximately the design that we came up with, right? We do have, in this example, for example, we had 168 pressure vessels, but in this image we have 160. So when you do design, there's going to be a few changes that you can make here and there. Maybe 160 would be better in order to reduce the number of pressure vessels. However, 168 could be better if you're worried about the second pass average flux, right? So there are little changes that you can make here and there to better suit your system depending on what requirements you have. So our design, it met the permeate quality at the worst case conditions, which was 8 trains, 35 degrees Celsius, and 3 years average membrane life, so the maximum membrane age. So our blended TDS, we met with 150 ppm, and it was a limiting, and we did include a safety margin of approximately 30%. So we did target around 115 ppm TDS, so we do have safety margin on that. And our blended boron, less than 2.4 ppm, we were well below 1.85 ppm with the safety margin as well. So we used high rejection, high flow membranes to minimize energy consumption in the first pass. We did consider a hybrid in order to remove flow warnings if they are a concern for your system. In this case, we're just making the assumption that it would be acceptable. However, this is going to be, again, depending case by case. Some systems, it might be more acceptable, while others operating with warnings would be a big concern, for example. We also used a partial permeate split, which allowed us to maximize the permeate split and also minimize the second pass size, right? So with the simple split method, you wouldn't be able to use as high of a permeate split. We also accounted for the N-1 operation. So the train, the operation works with both 8 trains as well as 7 trains. We did use a little bit of permeate back pressure in the second pass first stage in order to manage some of the high lead element flow. Again, this is a case-by-case thing. In some cases, maybe the client doesn't want any permeate back pressure. And in other cases, it's okay to consider a little bit. And again, also we have energy recovery device with 6% volumetric mixing, and and the second pass brine recirculation is also included in our system. And one of the things we did do was we checked that the worst case quality and feed pressure with our membranes at max membrane age, and we also checked the new membranes at membrane age 0 in order to see if there's any potential flow or recovery operating issues, which we did note. And in this case, we noted that we're okay. But again, in other cases, maybe we want to use a hybrid in order to remove those warnings.